Hello students, we are in the fourth module now. This is the last module of the course. In this module we are going to look at some of the software optimizations with an understanding of the underlying hardware that we have already done in our module 1, 2 and 3. In module 1 we understood the notion of ISA and how assembly code is generated. In module 2 we understood how these assembly instructions are executed, and in module 3 how the data and instructions are stored in a hierarchy of memories. So I hope you will be able to connect the dots in this module, and I hope this will also help you to optimize your programs better whenever you write from now on. So let's dive in. So this is one of the basic requirement that a program should run correctly under all conditions. It means that if we introduce some optimizations which will help the program run faster, but if it gives wrong results, it's of no use at the end. Nobody is going to deploy that. So whenever we talk about program optimizations, correctness is of utmost importance. Now, considering that as our ground truth, how do we write efficient programs? The very first thing is to select an appropriate set of algorithms and data structures. Second is write a code that the compiler can optimize effectively. Compiler has lot of other actions to perform. We have seen a couple of them during our module 2. So in addition, if we are able to give the compiler possibility of us generating more independent instructions, so probably it can do some code reordering, so on and so forth, to reduce the hazards and all. The third important point of writing efficient algorithms is to visualize the program as if you are going to run it on multiple cores and multiple processors. Of course, the program itself is to be having enough parallelism in it to do such a thing. And till 2004-5 time, the time frame where we moved from single core to multi-core, this point was never given much of a thought. Only parallel programs were written for some huge scientific applications because they work on huge data and they take a lot of time to run. So only those scientists who are working on those programs or applications used to spend time parallelizing it. But now this is something we need to have by default. Whenever we set out to write a program, if we are able to visualize it as if it's going to be run on more than one core, it will help in the overall execution time. So this is called concurrent programming. Another point to think about is whether as a programmer we should go for an easy to implement application or algorithm, or an algorithm which will eventually lead to good speed up. So to quickly relate to, if you want to sort an array of elements, insertion sort is one of the simplest sorting algorithms that we can implement. On the other hand, a divide and conquer algorithm like a merge sort is quite challenging when compared to insertion sort. But if we look at the speed of both these sorting algorithms, it's a no-brainer that merge sort will outplay insertion sort. That was the reason it was proposed to begin with. So programming complexity should be not your primary concern. If you want your program to run faster, you need to spend more time and write it with better algorithms. Also, there might be many optimizations that we introduce to optimize the program eventual performance that might lead to a reduction in code readability or modularity. So here we need a diligent thought process on which optimizations can help us or which optimization we can afford. After including few of these optimizations, the end program can be difficult to debug or modify or extend because it might have limited modularity. So this is a trade-off. Again, code maintenance will be challenging when we go for efficient program optimizations. In addition, modern compilers employ a lot of sophisticated analysis and optimizations during the compile time to generate a very efficient machine code. So I'm assuming that even the assembler is part of the regular compilation. But these compilers have limited scope and they have difficulty with few optimization blockers. We are going to discuss them as we go. These optimization blockers are dependent on the current execution environment, which can be the variables or the set of inputs, so on and so forth. So here the programmer's knowledge of the underlying hardware or the nature of program itself can help us better to optimize the program. A quick uh, view about some of the capabilities and limitations of the optimizing compilers that we have currently. These compilers convert the high level language code to the machine code very efficiently. That means they are very good with register allocation and data reuse, mainly to reduce register spilling. They are pretty good with the code selection and ordering of the eventual instructions. In addition, they can also handle some minor inefficiencies with the code that has been written. So you will be exposed to these topics much more in detail in your compilers course. Also, there are compilers which come with multiple optimization levels that we can select during the compilation time. For example, GCC comes with 3 levels of optimization: O1, O2 and O3. You can specify that at the command line when you are compiling the program. In fact, you can take any regular matrix multiplication program that you would have written, compile them with these 3 optimizations. You will get 3 different binaries, run the binaries and see overall time each one is taking. Even though the compilers have a lot of optimization features in them, they might not help us with improving the overall asymptotic efficiency. That is primarily dependent on the algorithm we choose. For example, if we have chosen insertion sort, the compiler will not replace it with a merge sort. Let's say the time complexity for the insertion sort is C1 times order of n square. So we know that there is a better algorithm here, for example merge sort, so we employed it, and let's say the time complexity is C2 times order of n log n. So we have reduced from n square to n log n. So these are the big O savings that you are already aware of. This will have a big impact on overall runtime of your program. But the constant factors here, C1 and C2, should not be neglected either. For example, here is a small graph with the number of elements to sort on the x-axis and the overall time in microseconds for sorting. And I have taken the merge sort time complexity, and for different constant factor values from 1, 1.5, 2 and 2.5, I have just plotted the rough time it would take. Now, if we consider this particular data point for 1 million elements, if you want to sort, if the constant factor is 1, it would roughly take 6 microseconds. But if the constant factor is 2.5, it would take almost 15 microseconds. So it's just to explain a little more graphically, I have plotted this. So you see that based on the input, typically huge inputs, the constant factor has lot of say on overall execution time. And here comes the underlying architecture. It would determine the constant factor. So in your regular algorithms and data structure courses, you would mainly focus on algorithmic complexity, and you would abstract out all the system level details. But hopefully, with the current understanding of the architecture and eventually with operating systems and compilers, you'll be able to appreciate the effect of these on the overall execution time. So coming back to the optimizing compilers, they have difficulty in overcoming the optimization blockers. I've already mentioned that. The two optimization blockers are memory aliasing and procedure calls. We are going to look at them with a couple of examples now. So whenever compiler is thinking to optimize the program, it has to do it safely. It should not generate a code which will give wrong results based on the inputs. So to eliminate any possible undesirable behavior at runtime, the compilers most of the time go for conservative optimizations. They do not take any risk because they don't know the runtime behavior of the program. So here comes the programmer's influence to help the compiler to generate a better code. Let's look at an example. Here we have Twiddle1 routine. It has two integer pointers, xp and yp, and all it's doing is it's incrementing xp by yp twice. Now we can probably replace it with a another function twiddle2, where we are directly incrementing the xp by twice yp instead of doing in two steps. So if we eventually run this program, probably twiddle2 would run slightly faster than twiddle1. But is twiddle2 a safe optimization? If we consider the corner case where xp and yp are equal, twiddle1 would generate a value which is 4 times the xp, but twiddle2 would generate a value or return a value which is 3 times xp. So the correctness of the program is compromised here. So from the compiler perspective, this is the memory aliasing problem, wherein at the runtime we cannot decipher whether two pointers are pointing to the same location or not. So even when we were discussing the data hazards, I have mentioned this, saying that if we have the address of a load instruction dependent on prior calculation, and if that calculation is changing at runtime, then we cannot expect or understand its impact on the subsequent instructions in case both of them are pointing to the same address or not. So program reordering, the instructions reordering in with such tricky instructions is not possible. The same case with the compilers. In case the compiler cannot determine that there will not be any memory aliasing, it will not go for any code optimizations. So this is the first optimization blocker. Let's look at another example. Here we have a function called function1, which is in turn calling another function f 4 times, summing them up and returning that value. Now we can think about replacing function1 with another function2, which directly returns the value 4 times the value given by function1. It might look a trivial optimization, but there is a catch. They are not same because they are dependent on the function f itself. For example, if you have a function f which is affecting a global variable here counter, at the end of function 1 and at the end of function 2, the value of counter is different. That means the return value of function 1 and function 2 would also be different. So this is not a valid optimization again. The only possible solution that the compiler has in this scenario is to replace the function f with its actual code, the inline substitution. But as you are aware, inline substitution increases the overall code size, so it has very limited scope. You can try this out by giving O2 optimization level in GCC, or you can explicitly set the flag -f inline to invoke this inline substitution for your program at the compile time. So this is the second optimization blocker. The compiler cannot upfront decide on the role of the procedure and what all other variables it might impact. So again, the compilers will be very conservative and they do not optimize any function calls. So with that quick understanding of the limitations of the current compilers, let's look at what all optimizations are possible from our end as programmers. The very first step in optimizing program is to avoid any redundant work. It can be unnecessary function calls or condition checks or memory references. Another step is to visualize how the underlying processor is working. Basically, pipelining way of execution wherein it's not that only one instruction is being executed at a time. At any given cycle, there might be multiple instructions that are being executed. So the dependency among these instructions will come into our picture and we should try to reduce the dependencies. That will help us to reduce the overall data hazards. In addition, if we visualize how the data is moving in and out of the processor pipeline to the caches using the load and store instructions, and because the caches have limited size and whenever there is a cache miss we need to stall the pipeline, so on and so forth, we can try to reduce unnecessary load and store instructions. The third step is to look at the code where the program spends most of its time in execution. It means that we should do a trial run of the program, popularly called as profiling. When we do that, we will know the blocks of the program where most of the time was spent. Now we need to specifically focus on that portion of the code and optimize it further. So with all these small steps, the eventual program code that is generated and run will be much faster than an unoptimized program. So let's look at the different program optimizations. First one, let's try to understand with one example. So let's say we have two for loops, I loop and j loop, and we are doing some array accesses and trying to assign values to some element of array A to some element of array B to an element of array A based on some index calculation. So the main observation here is the value n times I is same for an iteration of I and all the iterations of j. But with the current code, n times I gets calculated every time. So we can simply avoid that by calculating the n times I. Let's say we have introduced a new variable ni, which is just n times I, and we are using that variable inside the j loop. So we have replaced in multiplication instruction, or rather we have avoided a multiplication instruction completely to generate the index of A. So this is called code motion, wherein we reduce the frequency of those computations which will not change across multiple iterations or function calls. This point will not be so straight, so it's quite straightforward for us programmers, but it's not so simple for the compiler. It will not be able to detect such a simple optimization. Typically, loops are the the code blocks where a lot of time is spent. So it's better to look for such optimizations in the loops. So here, just because we moved a multiplication from the J loop, we have reduced the number of overall multiplicative instructions by almost n square, or oh sorry, it's n times. Another example, let's consider a vector data type. Let's say it has two variables, length len and a data pointer to the actual array of elements of length len. So this is how the structure would look like. The elements which are stored here, it's given as data underscore t, can be any of the integer or float or double. When you write the program, you can stick to one of them and write the code. Let's say this vector has couple of utility functions. The first one is get vector element. It expects the arguments, the actual pointer to the vector, the index of the element it's looking for, and the dest variable to which this indexed element should be assigned. So the very first thing that we would do is to check the boundary conditions. If the index is out of bounds, then we would return a 0. Otherwise, we return the element. Another utility function can be to get the vector length. It would accept the vector itself as an argument and it would return len, which is the length of the vector. Now let's say we write a small function combine1 which will perform some operation on the array of elements. For example, we want to add all the elements. So in that case, the op here would be plus and ident would be 0. This is the starting value. If you want to multiply all the elements, then op will be multiply and ident would be 1, the starting value. So within this function, we are iterating the for len number of times, and we are checking if the current iteration is less than the length of the vector or not. If it is less than, then we retrieve that element with the index as I, and to that, so that element will be added or multiplied to the dest element, dest. So this looks pretty much straightforward code. All we are doing is to check the condition and get the element, add or multiply it. Now if we observe, we are calling the utility function vector length for each iteration of the loop, and we know that, okay, so we are also calling the function get vector element in each iteration of the loop. The key observation here is the function called vector length will return the same value across the multiple iterations. So it's better to avoid calling the same function if it's returning the same value. So if you want to look at it from the execution point of view, every time there is a check to get the vector to compare with the vector length, what we do is the vector length itself would be a procedure, and we need to include a branch or a jump statement there. In the procedure call, we would return with the length of the vector back to the main program, There we would do a comparison, and only when the comparison is valid or the output of comparison says that the index is less than the current vector length, we would do the remaining process. So you do realize that whenever there is a procedure, there is a control statement which would result in a control hazard. So if we are able to avoid such function calls which are returning the same value, it would be a lot of help at the runtime. So let's see how we can do that. So here is an optimized version of this combine1, which is combine2, wherein we are making only one function call. Again, this is an example of code motion. There is only one call to the vector length. We get that in the variable length, and we keep reusing the variable. And as you might have already guessed, whenever we are reusing the elements, they would be ideally sitting in the registers. So they are quite fast for the processor pipeline to access and work with. As we have already seen, compilers are very conservative whenever they look at the function calls. So they wouldn't ideally do away with such an optimization. This is where we can help it. So if such a small change looks very trivial to you, let's look at the common code that people write to convert a string of characters from uppercase to lowercase. So here is lower one, wherein we are checking the string length every time, and we are checking if it is in uppercase, then we are converting it to the lowercase and writing it to the same location. Pretty straightforward. And here is an optimized version with code motion. We are calling the string length only once and storing it in len. And when the system programmers ran it on the actual hardware, this is how the eventual behavior was. On x-axis we have the string length, on y-axis we have the number of seconds the programs took, and if you look at the time taken by lower 1 and lower 2, as the string length is increasing, the disparity is quite high. For example, if we have a string of length 500,000 characters, then lower 2 would take only few seconds, but lower 1 would take 180 seconds, which is a huge difference and huge performance benefit with a small change in the code. And here too, you can imagine the difficulty of the compiler. The compiler would see that the data in the string is changing, but it doesn't know that the length of the string is same. So it cannot do such an optimization. Even though it's quite trivial to us as programmers, it's not so for the compiler. Another related program optimization, we start with the combine2 code, wherein we move the vector length out of the for loop. We can reduce the procedural calls even further. Here the function call we are making to retrieve each element is for get vector element, wherein we are sending the index I, and the value of the element will be assigned to variable val that we are going to use right after. But if we get a pointer to the beginning of the array before we enter the loop, probably we can use the pointer to move across the array instead of making a function call. For that, we need to introduce another utility function here, get vector start, it takes the vector as input and returns the address of the first data element. So with such a function call at our disposal, here we have a pointer to the first element of this vector, which we are going to use within the for loop. So if you observe, we have totally removed the function calls within the for loop. All we are doing is accessing the DEST and elements of the array data. So this kind of abstraction or optimization is not so straightforward, and the programmer would need to spend some more time to figure out these things. But it's worth it because procedural calls are expensive. Also, the boundary checking is expensive. So if you remember, in the get vector element, we are checking the, the argument I here with whether it's in the range of the vector or not. But if we know that when eventually deployed that might not be the case, we can probably remove the boundary check. Boundary check is comparison, and you know that comparison will eventually result as jump or branch instructions. But it's not so safe. Only if you are 100% sure that the input in the final deployment will never go out of bound, probably we can skip that. Another program optimization. So this was the function call we did some code motion, and we said we'll calculate n times I beforehand and keep it ready. What better we can do is reduction in strength. Replace costly operations with simpler ones. So here the cost is in terms of the latency of the operations. As you are aware, a multiplier and a divider would be much slower when compared to an adder or a subtractor or shifter, the actual hardware. So whenever we can, we should avoid such costly instructions and try to replace them with a simpler instruction like shift or add. So for example, if you want to multiply an element x with 16, we can probably left shift it by 4 instead of using the actual multiplication. This will be much faster than using the multiplier in the hardware. So the initial code can now be changed into something like this, wherein we are incrementing the value of ni by n for each iteration of I. This is effectively same as multiplying n with I for each iteration. But if the underlying hardware says that all the operations will take same time and same power, this optimization might not be so effective with performance. So another related point is to share common sub expressions. Again, this falls in the reduction in strength only. Reduce or reuse the portions of expressions which are appearing at multiple locations. Again, compilers are not so good at identifying such common expressions because they don't have any analytical abilities to understand that two arithmetic expressions are same. So popular example in image processing is to average or get the value of a pixel based on some value in the neighboring pixels. So the neighboring pixels are left, right, up and down. So here we have a small function which retrieves the value which is above, up, down, left and right and sum it to generate the value of the current pixel which is at location I and j. Now this can be optimized by introducing another variable I and j with an expression I times n plus j. So if you observe I times n plus j is a common sub-expression among these four equations. So they are being replaced by a simple add and subtract instead of multiplication. So if you imagine these expressions part of a nested ij loops, we have reduced a lot of work by eliminating unnecessary multiplications in each iteration. The third, program optimization. So we'll start with the optimized code, wherein we remove both the function calls from the for loop. What better we can do is to eliminate unnecessary or unneeded memory references. So here the unnecessary memory reference is for the pointer dest. We would need to store the value of dest only at the end of this loop, not for every iteration. So we can introduce a temporary variable, let's say it's an accumulator acc, and perform the required add or multiply of all the elements and keep accumulating, and once we are out of that loop, this accumulated value can be finally assigned to the variable dest. As you already know, the acc variable here will be part or mapped to some register and reused across all the iterations of the loop. Just by replacing the dest pointer reference to with a local variable, we are avoiding one load and one store for every element or for every iteration of the loop. And as you are aware, if load and store are misses in the cache, they would take multiple cycles, and during this time the processor will stall. So overall performance will greatly improve with such a small change in the code. So with all such optimizations, if we want to look at how effective it would be, so this is from the reference book for this chapter. I'm going to share this the particular chapter also with you. The book is Computer Systems, A Programmer's Perspective by Bryant. It's the second edition, so it's not 6, it is E. So here the metric we are trying to compare with is the number of cycles required for processing one element, CPE. It's not a standard metric. Just for quick understanding, in this topic the authors have proposed for such a metric. So let's quickly go through the table. Here we have the first column, which is the method, which has 5 entries. Abstract -g is the combine one function. Abstract o2 -o2 is the optimization done by GCC. Move vector length, data access and accumulate in temporary register are combined 2, 3 and 4. Sorry. Excuse me. So they have performed experiments with different data types, integer and floating point, and different operations, add and multiply. So let's take the most costliest one here. The combined one was taking almost 160 cycles to process one element for a floating point array or array of floating points or a vector of floating points performing multiplication. And with all the optimizations included, it drops to just 5 cycles per element. So you can see how big an impact is if we are reducing unnecessary computation and unnecessary program calls or function calls. So with that, I summarize this portion of the module. We have seen three different program optimizations. The first one is code motion. The compiler is kind of reasonably good for code motion if we are considering simple loop and array structures, but not anything with any other complex data types. Also, they do not do well with procedure calls and memory aliasing, so the programmers need to identify such opportunities and move the code accordingly. The second optimization is reduction in strength, wherein we are choosing those operations which are faster to perform rather than a simple multiply or divide. Many a times the compilers are good at it, and the exact impact of such an optimization is machine dependent. If all the operations take same time, then this optimization will not give any specific advantage. But if we are able to reduce or reuse the common sub expressions and reduce the overall number of instructions, then it will be benefiting the overall performance quite a bit, and compilers have very limited role here. It's completely dependent on the programmers. The third optimization is to remove any unnecessary memory references. We as programmers who have now the understanding of underlying hardware, wherein we know that there is a pipeline where multiple instructions are being executed and the data will be brought from caches, DRAM, or eventually from the secondary memory, we need to try and reuse the data that we have brought as much as possible, and need to remove any unnecessary load and store instructions so that the overall stalls in the pipeline will be less. Again, the compilers take a conservative approach in order to avoid any memory aliasing problem. So it's up to us as programmers with an improved understanding to go for such an optimization. So I'll conclude this lecture now, but before that, it would be very interesting if you try out implementing the 4 functions, combine 1, 2, 3, and 4 along with all the necessary utility functions, write their RISC-V code and run it on your RISC-V simulator that you have built as part of course project. Therein you can actually see the total number of dynamic instructions that got executed, the number of cycles it took, and of them how many stalls were there, so on and so forth. You can have a hands-on experience on how effective each of these optimizations can be. So try it out and let me know if you have any doubts or you found anything interesting to share with the class. So with that, I'll pause this lecture. Thank you.